Hello, welcome to my talk on basic mathematical equations for potential flow theory. In this talk, we will show how the fluid dynamic problems can be mathematically simplified under the assumption of irrotational flows. This would include both the incompressible and the compressible flows. In reality, the practical flows might be at high Reynolds numbers, and many flows or part of the flows can be regarded as irrotational flows. Under the assumption of irrotational flows, the flow velocity vector can be represented using a scalar function, the velocity potential function. This change would greatly simplify the fluid dynamics, in which we need to solve a scalar function, the velocity potential function, rather than solve the three velocity components directly. In addition, for many practical applications, the mathematical equation for the potential function would be fully linear or can be linearized for the practical applications. In this talk, we will see how we can mathematically simplify the fluid dynamic problems. As the most important and the must assumption, the flow is assumed to be irrotational. Mathematically, the core of the velocity vector is zero. This equation can be written in a form of determinant given by this, and in details we have the expression as this. To make sure this equation satisfied, all the components around the three axes must be zero. That is, we will have three equations for the three velocity components u, v, and w. So, under the hypothesis of a rotational flow, its three velocity components are no longer independent of each other, but linked by these three equations. We can see here we have three partial differential equations for three velocity components. Does this mean the rotational flow itself could form a complete system for the flow field? To answer this question, we look at an example for the 2D potential flow. In 2D, the zero core of the velocity vector would lead an equation as this. So here we have one equation for two velocity components u and v. Therefore, for 2D rotational flow, to solve the velocity component, we need an additional equation, and we will see the additional equation is actually the continuity equation, especially for the incompressible flow. So, we can see there is a conflict between 2D and 3D cases, because in 3D case, it seems the assumption of the irrotational flow itself would make a complete system. But for 2D case, we need an extra equation to make the complete dynamic system. Why we have such a conflict? In this slide, we will see why there is a conflict in 3D irrotational flows. In fact, all these three equations based on the zero core of the velocity vector, they are not independent. Here we can use the first two equations to derive the third one. Take the first two equations and differentiate the first equation with regard to x. So we have the expression as this. And for the second equation, the differentiation with regard to y, we have this. So we can see these two terms are same. Therefore, we can obtain an equation as this. This equation can be written as this. Integrate this equation, we can obtain an equation as this. Here, c is the integral constant. If we take a c equaling to 0, and then we can see this equation is exactly same as the third equation. These three equations based on the zero core of the velocity vector are not independent of each other. And this means we need an additional equation for completing the dynamic equation in 3D irrotational flow. And we will see the additional equation would be the continuity equation. As such, we can see in both 2D and 3D cases, we need the continuity equation to complete the equations for the fluid velocities in the irrotational flows. For the potential flow, the hypothesis of an irrotational flow means an existence of a velocity potential function phi, and the velocity vector v can be calculated as the gradient of the potential function phi. And if we calculate the velocity vector from the velocity potential function, and the core of this velocity vector would be calculated as this, and we can see the core of the velocity vector would be 0. This is the proof for the existence of the velocity potential function. In the Cartesian coordinate, the three velocity components are calculated given by these expressions: u along x-axis, v along y-axis, and w along z-axis. So all these three velocity components can be determined by the potential function phi only. If the flow velocity is not very high, for instance, its Mach number m is less than 0.3, and the fluid can be considered as incompressible. This can be expressed by the mathematical expression for the continuity equation given by this. The divergence of the velocity vector is 0. So applying the potential function to the continuity equation, we have the expression as this. And this part is an equation called Laplace equation. This is a simple linear partial differential equation. In details, the Laplace equation can be given in this form, and here the Laplace squared is called the Laplace operator given in this form. So here we can see the problem of three velocity components are degraded into the simple linear Laplace equation for the velocity potential function phi. In 2D, the Laplace equation is given as this. So we can see the Laplace equation is the second-order partial differential equation, and that can be solved if the corresponding boundary conditions are specified. For solving the Laplace equation, we generally have two different types of boundary conditions, namely the kinematic boundary condition and the dynamic boundary condition. For the kinematic boundary condition, we may specify the velocity of the fluid on the boundary. The most applied one is the no penetration condition, as the relative normal velocity between the body surface and the fluid motion are zero, given in this equation. Here, n is the normal vector, and the vector Vb is the body motion velocity. For a fixed structure, Vb would be zero. And this boundary condition can be written as the form as this. This is the form we normally see in many textbooks and published papers. And for the lifting bodies, if the fluid is taken as Inviscid, so to generate the correct lift, Coulter conditions must be applied, which would be given at the trailing edge of the airfoils or wings. For instance, the Coulter conditions given at the trailing edge of the airfoil for the normal airfoil and for the cusped airfoil trailing edge, as I talked in the thin airfoil theory. The second boundary condition is the dynamic boundary condition, for which the forces on the boundaries is specified. For instance, for the problem of free surface, and the pressure on the free surface must be same as the atmospheric pressure, P0, given by this. Here, I must say, in most cases, the kinematic boundary conditions alone would be enough for solving the Laplace equation. Up to now, by solving the Laplace equation with the relative boundary condition, we can calculate the flow velocity in the flow field. It seems we haven't used Navier-Stokes equation or Euler equation in the irrotational flow yet. Can we say we have solved the flow dynamic problem without Navier-Stokes equation or Euler equation? The answer for this would be yes and no. If you are only interested in the fluid velocity, yes, the problem is solved. However, the fluid dynamic problem is more for finding the forces and the moments of the fluid acting on the structure. For instance, for flying an airplane, you must generate enough lift to balance the airplane weight. For achieving that, we need to use Navier-Stokes equation or Euler equation to build the link between the velocity and the fluid pressure, normally in a form of Bernoulli's equation. For irrotational flows, the Bernoulli's equation can be derived from Euler equation, given as this. Here, the fluid body force is given by rho g vector k. Here, we choose the coordinates with positive z pointing up. The difficulty in the Euler equation is the convective acceleration, but we can use the vector calculus identity given as this. So here, if we take the vector A and B same as the velocity vector, so we have the expression as this. Consider the irrotational flow. The core of the velocity vector would be 0, so this term would vanish. Therefore, we can obtain the convective velocity given as this. Here, we use the velocity potential function for representing the velocity vector. Therefore, for the rotational flows, Euler equation can be written in this form. Here we can see both sides of the equation are in differentiation forms. So we can integrate this equation. We obtain the Bernoulli's equation given in this form. Here, C0 is the integral constant, which would be specified for different applications. This Bernoulli's equation is a general Bernoulli's equation for irrotational flows, and it can be simplified based on the actual applications. For instance, for the steady flow, the first term would vanish, and for linearized flow, the second term, this term would be dropped, as we have seen in the wave structure interaction problem. And the fluid body force term, rho gz, would be only important for the structure like balloons floating in the air. Based on the equation for incompressible flows, given as the divergence of the velocity vector is 0, and from which we can define a stream function, a vector, capital psi, which has 3 components, psi 1, psi 2, and psi 3. And the relation of the stream function vector and the velocity vector would be given as this, and it is calculated in a determinant. So if we put it in details, we have the expression as this. So based on the stream function, we can calculate the divergence of the velocity vector here. So we can see the divergence of the velocity vector is 0. This means the stream function, the capital psi, would satisfy the incompressible flow condition. However, the stream function itself is a vector with 3 independent components. In this regard, the stream function would not provide much advantages over the velocity vector in practical applications. And if we compare the potential function, which is a scalar potential function with only 1 component, versus the stream function vector, which has 3 components, so we can see the potential function would have huge advantages over the stream function. However, stream functions can be very useful in 2D cases, and some of them are extremely useful. See the next slide. In 2D case, we can assume the velocity component W as 0, and this means the stream function would have only 1 component, 1 non-zero component, given as this. So the first and the second component are both 0, only the third component is non-zero. And based on the definition of the stream function, so we can calculate the 2D velocity component u, given by this and this. And here we will see 2 important results for 2D stream function. Consider the stream equation that would be given by this. So this equation can be written as this, and substitute the velocity component defined by the stream function. We could have the expression as this. So this expression means the stream function is a constant on any given stream line. So another interesting fact is in 2D case, the dot product of the gradients of the potential function and the stream function would be 0. So we calculate this dot product. We substitute the component of the gradient here and here. Time this together, we have the expression as this. And substitute the velocity component defined by potential function and the stream function. We have this expression. It is 0. So in 2D, we can see the fluid stream function are always perpendicular to the equal potential lines. So in this plot, we can see the black circles are the equipotential lines and the red are the stream lines. So we can see these two lines are perpendicular everywhere. This is the plot we can see in many textbooks. And in the application of the potential flow theory, these two conclusions would be very useful in the study of the simple potential flows. We will see some examples in other talks. In many cases, for the potential flows, the fluid is assumed to be incompressible. However, potential flow theory is also valid for compressible flows. Here, we will examine the case. For the steady compressible flow, the continuity equation can be expressed as this, and the more detailed expression would be given as this. So for the air, we can calculate the speed of the sound under the assumption of isentropic process. So the equation is given as this. Here, P is the pressure, and rho is the density of the air, and A is the speed of the sound. Now, we can use the Bernoulli's equation for the steady flow, and we drop the body force here. So the Bernoulli's equation is given by this expression. So we can calculate the dP given as this. Here, we note the actual pressure change is mainly caused by the velocity potential here. In fact, this expression can be obtained from the Euler equation directly, but for simplicity, we use the Bernoulli's equation. As such, we can obtain the density change d rho given by this expression. Based on the relation we obtained in the previous slide here, we can calculate the density differentiation with regard to x given as this, and we can obtain the expression as this. Similarly, we can calculate the differentiations of the density rho with regard to y and z. So all these calculations are very similar. So if we substitute these expressions into the continuity equation here, and we can obtain the general potential equation for compressible flows. Obviously, this potential equation is much more complicated than the Laplace equation for incompressible flows. And this equation is a nonlinear partial differential equation. For practical applications, we may be able to simplify the potential equation. For instance, if we are interested in the flow past the thin airfoil at small angles of attack, see the plot here, then the problem can be much simplified. In here, we can take the total velocity potential, capital phi, as two parts. Phi 0 is the potential for the undisturbed incoming flow, and phi is the disturbance potential, and the corresponding velocity potential is given by these two potentials together, and the corresponding velocities are given as this. The incoming flow is from x-axis, while the disturbance velocities u prime, v prime, and w prime are superimposed on the uniform flow. See the plot here. And the total velocity can be expressed as this. So in details, we can obtain the relation for the velocity component along x-axis, y-axis, and z-axis respectively. To simplify the potential equation, we examine the magnitude of the velocity component. The velocity component along x-axis u is given by u0 plus u prime, but the disturbance velocity u prime is much smaller than u0, which is comparable to the speed of the sound a, while the speed along y-axis and the z-axis would be the disturbance velocity component v prime and w prime, which are both much smaller than the speed of the sound, because the flow passes the thin airfoil and the small angle of attack. The disturbance would be quite small. So consider the magnitude and drop the terms of small value. We can have the equation as the linearized potential equation for compressible flows, given by this equation. Here, m0 is the Mach number, defined as the ratio of the incoming flow velocity over the speed of the sound. And based on the reference, so this linearized potential equation for compressible flows would be valid for both subsonic flows of Mach number between 0.3 and 0.8, and the supersonic flows of Mach number between 1.2 and 5.0. Here, we look at the coordinate scaling for subsonic flows when the Mach number m0 is smaller than 1.0. Thus, we can define a coordinate scaling factor beta, and the corresponding coordinate scaling given by x bar equaling x, y bar equaling beta y, and z bar equaling to beta z. And we can calculate the differentiation phi with regard to x, so we can obtain the relation as this. For the differentiation of the potential with regard to y and z, the relation is slightly different from the relation here, so we get the beta here. And similarly, we can calculate the second order differentiation given by this for the differentiation with regard to x. And the differentiation with y, we can calculate this, and the differentiation with regard to z. So, if we substitute all these relations into the linearized equation, we can obtain the expression as this. And if we cancel out the term beta squared, we can obtain the scared potential equation for compressible flow. This is actually a Laplace equation. One interesting issue here is the coordinate scaling for such a compressible flow. Taking airfoil as an example, NACA 0009, we can see the coordinate on x-axis would be same, but the coordinate on y-axis would be reduced because the scaling factor beta here. In the drawing, the Mach number is taken as 0.75, and we can see the transformed airfoil would be thinner than the original airfoil. In the textbook of Anderson, Fundamentals of Aerodynamics, if the transformation is made for both the coordinates and the potential function, see this expression. In 2D case, the transformed potential equation would be given as the Laplace equation, as this. However, an advantage of such a coordinate scaling and the potential function scaling would mean there is no change in the shape of the airfoil in terms of the potential function. Thus, the same boundary conditions can be applied. As we have mentioned, the linearized potential equation is also valid for supersonic flows when Mach number is between 1.2 and 5.0. For the supersonic flows, we can see m0 would be larger than 1.0. Therefore, this factor 1 minus m0 squared would be a negative value. So we can define a different factor lambda given as this, and the corresponding potential equation would be given as this. So if we compare this equation to the potential equation for the subsonic flows, this equation is of elliptic type, and the equation for the supersonic flow is the hyperbolic type, which is in a way very similar to the wave equation. If we look at the potential equation for the supersonic flow in 2D case, it would be an equation as this. Obviously, this is a wave equation, and such a wave equation would have a general solution given by phi equaling the function of x minus lambda y. So if we apply this potential function into this potential equation, we can see this potential would be correct for this equation. However, this is not the specific solution. If we apply the relevant boundary condition, we may obtain the real solution. But in 3D case, the situation would be much more complicated. Thus, special treatment and numerical solutions may be needed, as shown in the reference 2.